The important thing is not to stop questioning. Curiosity has its own reason for existence. That's Albert Einstein, of course. And his words really set the stage perfectly for what we're diving into today. Welcome, curious minds, to the deep dive. Today we're tackling, well, a real heavyweight in physics. It's a problem that's puzzled scientists for, over a century? And it involves Einstein himself, plus a brand new paper that claims to unify some really fundamental laws of the universe.
That's exactly right. For about 120 years, this key idea in thermodynamics, Nernst's theorem, it sort of stood on its own, like an independent principle.
Mm.
But yeah, this recent breakthrough suggests maybe it's not separate at all. Maybe it's just a direct consequence of something we already knew.
Yeah.
It's a really fascinating look at how science evolves. How established ideas get re-examined.
Okay, so our mission today is to unpack this whole scientific revelation. We'll look at the history, understand this ingenious new solution, and figure out what it means for how we think about, temperature and energy. So whether you're maybe a student prepping for exams, needing that deeper grasp, or just someone who loves a good scientific aha moment, this deep dive is definitely for you. We're drawing our insights today from a pretty groundbreaking paper published in the European Physical Journal Plus.
Right.
Okay, let's get into the history then. Where does this story start?
Well, it kicks off in the early 20th century, a really exciting time for physics. Scientists were digging into how matter behaves at incredibly low temperatures, near absolute zero.
Absolute zero. That's minus 273 Celsius, right? 0 Kelvin. Just unbelievably cold.
Exactly. So cold that atoms basically just almost stop moving. And this is where Walther Nernst comes in. He was brilliant, actually won the Nobel Prize in Chemistry in 1920 for his work in this area.
Okay, so what did Nernst find down there at those crazy low temperatures?
What he observed, experimentally back in 1905, this became Nernst's theorem, was that entropy exchanges, the measure of disorder or randomness, they approach zero as the temperature gets closer and closer to absolute zero.
Entropy, like things becoming less organized. So at absolute zero, things just don't get more disordered.
Pretty much. That tendency for disorderliness just vanishes as you approach that limit. Now, to explain why, Nernst came up with this really compelling argument in 1912. He basically reasoned that absolute zero must be impossible to actually reach.
Impossible, why?
His logic was, okay, imagine you could reach absolute zero. Then you could, theoretically, build an engine using it as a perfect coolant. And this engine, he said, could convert all heat into work. Perfect efficiency. 100%.
But that sounds like it breaks some rules.
Exactly. Nernst argued that would violate the second principle of thermodynamics, the famous one that says entropy, or disorder in the universe, always tends to increase. You can't have perfect efficiency. You always lose something to disorder.
Okay, so Nernst says absolute zero is unreachable because reaching it would allow an engine that breaks the second law. Makes sense.
Mm-hmm. But what's really fascinating is how Einstein reacted. Pretty soon after Nernst laid this out, Einstein challenged the reasoning about the engine.
Challenged it? How?
Einstein basically said, look, that engine Nernst is talking about, you can't actually build it. It's purely hypothetical, impossible in practice. So Einstein concluded it poses no real threat to the second law. And because of that, he argued Nernst's observation that entropy exchange goes to zero wasn't a consequence of the second law, but had to be a third, independent principle of thermodynamics.
So Einstein separated them. He said Nernst's finding was its own law, the third law.
Precisely. And that view, that interpretation, is pretty much held sway for well over a century. It's what you find in most physics textbooks, a distinct third pillar of thermodynamics.
Okay, so that's the setup. Nernst's observation, his reasoning, Einstein's counter, and the resulting third law. But now, that's being overturned.
Yeah, here's where it gets really interesting. That 120-year-old interpretation. It's now been, convincingly challenged. Professor José María Martín-Olalla at the University of Seville published this paper arguing that the third principle, Nernst's theorem, actually follows directly from the second principle.
Directly, so it wasn't independent after all.
That's the claim. It's a huge potential simplification, right? Merging two fundamental laws into one, essentially.
How does he demonstrate that? What did Nernst and Einstein miss?
Well, Professor Martín-Olalla points out two crucial nuances that seem to have been overlooked in that original debate. First, he argues that the formal statement of the second principle itself, it actually requires the existence of that very engine Nernst imagined.
Wait, requires it? So Nernst's hypothetical engine isn't just hypothetical, it's somehow embedded in the second law.
According to Martín-Olalla, yes. If you look at the deep mathematical structure of the second law, It sort of implicitly predicts or necessitates the conceptual possibility of such an engine operating at absolute zero.
Wow, okay, that's a big shift. What's the second nuance?
The second nuance is that this required engine must be virtual.
Virtual, meaning not real, like a thought experiment tool.
Exactly. It doesn't consume heat. It doesn't produce work. It's purely conceptual, a logical construct within the theory. And because it's virtual, it doesn't actually violate the second principle in any practical way. It doesn't question the law.
Okay, let me see if I've got this. The second law implies this virtual engine exists conceptually, and because it's virtual, it doesn't break any rules.
Right.
So how does that connect back to Nernst's theorem?
By combining those two ideas, the necessary existence of the virtual engine from the second law and its virtual nature, Martín-Olalla can then mathematically derive two things. First, that entropy exchanges must tend to zero as temperature approaches zero, which is Nernst's theorem.
Oh.
And second, that absolute zero must be inaccessible. So it links Nernst's observation directly back to the second principle, solving that 120-year-old puzzle of whether it was independent or not.
So Nernst was sort of right about the consequence, inaccessibility, but maybe his reasoning about the physical engine violating the second law wasn't the core issue. It's this virtual engine required by the second law that leads to the conclusion.
That seems to be the essence of the new argument. It provides a much more, let's say, elegant and unified picture. It shows the third law isn't an add-on, but emerges naturally from the second.
This is fascinating. But it sounds like it also touches on how we even think about temperature. You mentioned distinguishing sensation from the physical quantity.
Exactly. That's another key part of Martín-Olalla's paper. He points out that in the historical debate, temperature was often treated as, well, an empirical thing, something you measure like pressure or volume that just happens to go to zero in extrapolation.
Like reading a thermometer, basically.
Kind of. But Martín-Olalla argues that the second principle, especially when you formalize it using this concept of the virtual engine, gives you a more fundamental theoretical definition of the natural zero of temperature.
So absolute zero isn't just the point where thermometers read zero. It's defined by this theoretical virtual engine concept inherent in the second law.
Precisely. It grounds absolute zero more firmly in the fundamental theory rather than just observation. And this different conceptualization of temperature's 0 point radically changes how you prove the theorem. It gives it a stronger theoretical foundation.
Okay, so this potentially unifies the second and third laws. What about other things happening near absolute zero? Are there other phenomena still considered separate? Like what about heat capacities? Don't they also go to zero?
Good question. Yes. The study notes that the cancellation of heat capacities, the fact that how much energy it takes to raise the temperature of something, also drops to zero near absolute zero. That's something Nernst also noted back in 1912. And Martín-Olalla acknowledges that this specific property can't seem to be directly derived from the second principle alone in the same way.
Ah, so maybe there is still something independent there.
Well, Martín-Olalla proposes a different way to look at it. He suggests that the second principle, through the derivation we just discussed, already implies that entropy has a unique value at absolute zero. The cancellation of heat capacities, he argues, simply adds the information that this unique entropy value is specifically zero.
So not a whole new principle, but more like setting the constant, important detail or an appendix to the main idea derived from the second law.
Exactly. He frames it more as an important appendix rather than a truly independent third principle. It suggests maybe the whole field could be simplified even further. Of course, he himself points out, academic inertia is a real thing, getting widespread acceptance for this kind of shift in thinking. It takes time.
Yeah, changing textbooks written for a century is probably not easy.
Definitely not. But the argument is out there now, and it's compelling.
So, stepping back, what's the big picture takeaway here? This work seems like a really significant step towards maybe a cleaner, more unified understanding of energy and entropy.
I think so. It simplifies the fundamental laws of thermodynamics, showing that what we thought was a separate rule is actually embedded within another, more fundamental one. That's always a sign of progress in physics, finding deeper connections.
And for listeners, especially maybe students grappling with these concepts, it's a fantastic example of science in action, isn't it? That even core principles aren't set in stone forever.
Absolutely. It's a powerful reminder that understanding evolves. Long-held beliefs, even ones associated with names like Einstein, can be revisited, refined, even overturned with new analysis and insight.
Which makes you wonder, right? What other scientific principles or laws out there that we currently treat as separate might actually be connected in ways we haven't figured out yet? Could there be more unifications waiting to be discovered?
It's entirely possible. That's the beauty of science. The questioning never really stops.
Well, we hope this deep dive has given you some fresh perspective on just how dynamic science is and the really profound work happening even in seemingly well-established fields like physics. If you found this deep dive as fascinating as we did, please do consider liking and subscribing to the deep dive wherever you get your podcasts. It really helps others find the show. And hey, if you have questions or maybe another complex topic you'd like us to tackle, leave a comment. We genuinely love hearing from you and seeing what sparks your curiosity.